Hello and good morning. Our presentation today is called the Deployed Quantal Response-Based Patrol Planning System for the U.S. Coast Guard. This is a partnership of the U.S. Coast Guard and academia. I'm Milind Tambe from the University of Southern California, and jointly presenting with me will be Fernando Ordonez from University of Chile and Katie Moretti from the U.S. Coast Guard. This is joint work with several postdocs and PhD students, as well as members of the U.S. Coast Guard, listed here on the first slide. So the outline of this presentation is we'll start by motivating the problem of patrols for the U.S. Coast Guard. We'll give background and modeling information. Following that, we'll go into quantal response and then get into algorithms, and that will be the part where Fernando will take over. And finally, when we come to evaluation of our system, Katie will talk about that. So the ports of the United States are responsible for $3.15 trillion of the U.S. economy. But there are threats to the port. For example, a boat bomb, as shown here with the USS Cole, sinking of large cargo ships, attack on oil tankers, and other threats to the critical infrastructure in ports. The U.S. Coast Guard is ultimately responsible for protecting these ports. To assist the U.S. Coast Guard, we've built a decision aid called Protect. The goal here is to provide the Coast Guard with advice on patrols, the kinds of patrols they should conduct in ports. Plans for patrols need to take into account the fact that different targets in the ports have different risks. And at the same time, an adversary can conduct surveillance and then respond, which means that the patrols have to be randomized to make them unpredictable. And at the same time, we have to take into account the fact that different targets, higher value targets, need to be protected more often, and take into account the fact that the adversary is going to respond to our patrol patterns. Protect has been in use in the Port of Boston since April of 2011 for planning patrols in that port. Since February of 2012, it's been in use in the Port of New York for planning patrols there. So these are patrols that are actually executed in New York. And the goal now in 2013 onwards is to roll out Protect to all of the ports of the US. So Protect follows on the heels of several applications of game theory that we've used, just as Protect is an application of game theory, in different venues. Our research started with the Armor application at the Los Angeles International Airport. There are 6 inbound roads into LAX, but not enough police officers to have checkpoints on all roads at all times. There are 8 terminals, but not enough K9 units to patrol all terminals at all times. So the question then becomes, where and when should the checkpoints be set up? Where and when should the patrols be conducted for the terminals with K9s? We constructed the system called Armor, which is based on this game theory background, which I'll get into a little bit later on. It's been in use since 2007 at LAX, so it's been in 5 years in operation and continuing. Following Armor came IRIS. This is for the Federal Air Marshal's Service. We are looking at international flights here. There are 3,000 flights daily, international, but not enough air marshals to be on every flight. So the question then becomes, which flight should have air marshals? So we do a randomized allocation of air marshals to flights, taking into account the fact that different flights have different risks. This system, again, based on same principles that I'll talk about later, has been in operation since 2009 and continuing on. While Armor and IRIS have been in operation, guards for the TSA and Trust for the Los Angeles Sheriff's Department are in evaluation mode. With guards, we are looking at protecting the airport with randomized security operations. With Trust, it is looking for ticketless travelers on trains in Los Angeles. Protect follows these applications, but there are significant new contributions in Protect. The first is efficient modeling of the patrol planning problem. Second is a departure from the perfect rationality assumption on part of the adversary that's embedded in all of previous work. A quantal response model, as I'll explain later, departs from the assumption that the adversary will maximize his expected value. Fernando will outline our research contributions in coming up with efficient algorithms, given that we have used a quantal response model. Now, evaluating the system is a complex matter, and we have several ways that we've tried to evaluate it. Katie will talk in more detail, but we've looked at simulations, looked at robustness of Protect in simulations. But beyond that, we've conducted actual evaluations where we've looked at real-world patrols before and after Protect was deployed. There was a mock attacker team, a adversary perspective team that looked at ports of Boston before and after Protect was deployed. And we've looked at all of those evaluations, which we will present in the latter part of this talk. So let's go to background and modeling now. The backbone of Protect is this Stackelberg games. Some of you may be familiar with Stackelberg games, but for the benefit of those who may not be, here's a simple example. A Stackelberg game is a leader-follower game where you have a defender, here the US Coast Guard, who's going to be the leader. An adversary is the follower. They're going to conduct surveillance and then react. This is a very simplified game that's being shown here. There's just 2 patrols and 2 targets in this port. Patrol 1 protects target 1. Patrol 2 protects target 2. If the Coast Guard were to always play a pure strategy of patrol 1, an adversary will observe that and attack target 2. The adversary gets a positive reward of 3, and the Coast Guard get a negative reward, -2. So any pure strategy, any deterministic strategy, an adversary conducting surveillance can defeat. If, however, the Coast Guard were to use a randomized strategy, a mixed strategy, so that they're 60% of the time at doing patrol 1 and 40% of the time they do patrol 2, an adversary conducting surveillance will only know that the Coast Guard are conducting patrol 1 60% of the time and patrol 2 40% of the time. But what they will do tomorrow remains unpredictable. The goal here is to increase the adversary's uncertainty and cost, and therefore improve the Coast Guard expected reward. Now, this is a 2x2 game, and I talked about coming up with 60-40 as the weighted random here, weights on the randomness here. But in reality, we are looking at a game with billions of patrol patterns and large numbers of targets, and therefore coming up with an optimized weight on the different patrols, the probability with which different patrols should be conducted, is a very challenging problem. And our contributions are coming up with fast algorithms to solve exactly this problem. Just to give you an illustration, here's the port of Boston. I've made up these patrol areas just for illustration here. The actual patrol areas are actually different, and there's more of them and so forth. But one patrol, for example, might visit patrol area 1, 2, and 3 and return. In different patrol areas, different activities may be conducted. A longer-term activity, an activity that takes more time, makes that particular target or set of targets more secure. But, of course, you're paying in terms of more time. There's a resource limit here as to how many hours you can do patrols per day. And therefore, now we have this trade-off of which patrol areas to visit in any given day, what security activities to conduct in those patrol areas. So we can list in a game all of the different possible patrols that the Coast Guard could conduct. I'm showing you here a very simplified game again with 4 targets, A, B, C, D, and 5 different patrol patterns. So in each patrol, so it's the first one here says we visit patrol area 1, 2, and come back to 1 and conduct these activities K1. But in other areas, we may do K2. So these are different activities that may be conducted. When there are billions of such patrols that are possible, obviously the game is very large. You notice here there are payoffs to the defender and the adversary, and that refers to the rewards and penalties for stopping an attack or a penalty for a successful attack. And depending on the level of security activity that's conducted, we may be more or less successful in stopping such an attack. Now, having this big game, of course, solving it becomes very difficult. So the first thing that we need to do is to construct a compact representation. And to that end, one of the things we notice here is that there's a lot of duplicates in this game matrix. For example, these 2 parts of the game matrix have identical payoffs for the 2 pure strategies of the defender. And that's because they refer to permutations of particular patrols. Similarly, there's duplicates here, again, because there are permutations of different securities, particular patrols. So we can construct a more compact game where we have eliminated these duplicates, which are permutations. And on top of it, we can look at patrols that are dominated. So in this case, this patrol is dominated by another patrol, which can be fit into the same time, but at the same time limit, but it accomplishes more security than the one that's been crossed out. So we eliminate dominated patrols, and now we're left with the compact game. So here's what we do. I've talked to you about constructing a graph of the different patrol areas within the Port of Boston, but we could do the same for other ports. From there, we construct this compact game matrix. Following that, we have an algorithm called PaySAC that will solve the game matrix. This generates probability distributions over the compact strategies. Then we expand these probabilities from these compact strategies to the full game, and then sample from that game to generate actual patrols that get executed in the Port of Boston or New York. So let me at this point turn to the quantal response model. The quantal response model leads to a relaxation of the perfect rationality assumption on part of the adversary. The perfect rationality assumption would say that the adversary maximizes his expected value. With the quantal response model, given a defender's mixed strategy Xi here, the adversary is going to select a target with a particular probability, which is given by this expression. The higher the expected value, the higher the likelihood that target will get selected, but a low expected value target does not have a probability of 0 of being selected, and that's the big difference. Lambda here defines the rationality level of the adversary. A lambda of 0 means the adversary will choose any target with uniform randomness. Higher lambda means the higher expected value targets will be selected with more likelihood. So we have a lot of results looking at the quantal response model against human subjects, comparing that with the perfect rationality model, and Fernando will talk about that. But at this point, let me hand this over to Fernando, who will talk about the algorithms, the research that had to be done in coming up with newer algorithms to solve a Stackelberg game given a quantal response model of a human adversary. Fernando.
Thank you. So thank you, Milind. We began essentially outlining 3 contributions that we did for on the research side to be able to solve these Stackelberg games with quantum response adversaries. The first contribution is actually formulating a mathematical programming problem that we see here, in which we are maximizing the expected leader reward, where the probability of the adversary selecting target I is given by the quantal response probability that Milind just outlined. So we're maximizing the leader's expected utility, and we're selecting with probability AJ the patrol pattern J. Okay, and that gives, when you sum it up, a certain coverage probability over different targets, which feeds into the utilities. Okay, we refer to this set of equations as the resource constraints of this model, and essentially, basically, what they are encapsulating or representing is the fact that the patrol patterns cannot just jump arbitrarily from one patrol area to another, but they actually have to come out of the base and visit patrol patterns in the order in which they appear in the port. This is a nice optimization problem. At least I like it. It has a polyhedral, nice LP feasible region. All the problem is in the objective function, which is non-convex and fractional. And the rest of our contributions are how we're able to solve this problem more efficiently. I mean, you can start giving this problem to a nonlinear solver, and you get a local optimal solution, and our computational results are going to compare against that heuristic. Okay, so our algorithms are essentially based in again, 3 ideas. The first is how to deal with fractional objective, and this is a fairly standard method in OR in which you use a binary search approach to narrow down the interval, upper and lower bound on the optimal value. And essentially, if you have a UL upper and lower bounds on the optimal value, to test the fact that the optimal solution is bigger than the midpoint, you can rearrange that to solve that optimization problem, nonlinear optimization problem. But if you see the objective function of that being less than 0, you know that there is such a point. There is a point that's bigger than the midpoint, and then you just raise the lower bound. On the other hand, if that's positive, then there is no such point, and you decrease the upper bound. This binary search procedure in logarithmic time will get you an epsilon optimal solution, problem is we're solving nonlinear, non-convex problems at each iteration. So those are the second two approaches. We take two approaches to dealing with that. The first is a nonlinear transformation. Luckily, this nonlinear transformation gives us a convex objective. And if we don't have any of these additional resources constraints, we're fine. We have a nice convex optimization problem. We have an overall polynomial time algorithm to solve, get within epsilon optimal of the objective function value. Unfortunately, the Coast Guard does have resource constraints because the patrol boats don't jump around. They actually have to move. Nice theoretical contribution for arbitrary games, but in practice we need to deal with this nonlinear objective function some other way. What we did here is we use a piecewise linear approximation. Okay, nice representation that leads to a mixed integer programming problem for which there are very good solvers nowadays. And essentially the integer variable that we need to use here is to represent the fact that the piecewise linear approximation uses a segment of these variables. We're approximating the coverage probability of every target. And to use a certain segment of the piecewise linear approximation, we have to make sure that the previous segments have been completely used. And here we're able to represent everything, but this is an approximation. And one of the computational results I'm going to show is that we don't lose much in the optimality value, and we gain a lot in the solution time. Okay. So in summary, our contributions in the research are this mathematical programming problem that allows us to represent, we believe for the first time, a Stackelberg game with a quantal response adversary. Then our algorithms are based on this binary search method, which reduces it to a polynomial time number of optimization solves. And then the first algorithm is a polynomial time algorithm that will get you an epsilon response, epsilon optimal solution to a Stackelberg game with a quantal response adversary for any matrix game. If the leader and the adversary are selecting arbitrary actions, this will get you the epsilon optimal solution in polynomial time. In practice, we have resources constraints, and then we have the theoretical contribution for PASAC, which is we can bound the error from the optimal solution by constants times 1 over k, which is the number of segments, and epsilon. So the more we increase the approximation, we're guaranteed to be getting an answer that's closer to optimal. And the epsilon is the tolerance of the binary search. This is by no means close work for us. In practice, we're continually thinking of new models to represent human behavior in games, especially how to model the behavior of adversaries. That would lead to other mathematical programming problems that we need to address. In addition, especially thinking of the deployment to all of the US, we're going to be facing with larger instances, larger ports, and different types of resources and actions that can be integrated into this, making the problem even larger. So we're still working on algorithms to solve this. Now switch to the evaluation. The evaluation is going to have two parts. I'm going to present the first three, which are more simulation and computer related, and then Katie will present the actual evaluation of the system of Protect by the Coast Guard. So I'll present three slides, well, a little bit more than 3 slides. But the first slide has to do with the benefit of using quantal response against human adversaries. These are the results, empirical results obtained with a computer program, a computer game that we use to play against students and on online Turk. So these are average results, not expected utility results, but the average results over many trials. For different strategies, we use quantal response. We use two models which assume the leader is perfectly rational, and we use models based on prospect theory, which is also a human behavior of game theory. And if we sum, we look at the expected, the average reward that we got over many trials, over many people for different payoffs, we see that quantal response tends to dominate. This is often with statistical significance, and this is one of the reasons why we chose quantal response. The second set of results have to do with PASAC and the accuracy and the solution time. Here, those big bars, which means very little reward for us on the objective value, this is the heuristic of solving the nonlinear fractional objective function with random restarts, with 20 and with 100. So it improves a little bit, but not much. But if we go to PASAC, for different number of intervals in the linear approximation, we improve the objective significantly from 5 to 10 and 20. And here's GOSAQ, okay, which would be the optimal in the absence of assignment constraints. But if we look at solution times, GOSAQ is much larger because it requires a polynomial number of optimization of nonlinear convex optimization problems. And actually, PASAC is, thanks to the very good work of people in integer programming, we have outstanding algorithms for that. So the time is meaningless. The last set of results, and he'll present 2 slides, have to do with the robustness of the assumptions we make in PASAC. Okay. For example, we assume that there's a lambda of 1.5, which has to do with the level of it's not risk averseness, of rationality, thank you, of rationality of the adversary. And if we assume that to be 1.5 and we compare it, with dogs, which assumes a perfectly rational adversary, we obtain a much larger reward for lambda 1.5, but maintain that even up to lambda of 3.5. When lambda becomes very, very large, we're essentially dealing with a perfectly rational adversary, and we should use a perfectly rational adversary. But if in addition there's errors or noise in the game, and for example here we present results with observation noise, which means that we implement a strategy, but the adversary misinterprets it while observing it and assumes, oh, we're doing something a little bit different, then our rewards are much better than the rewards that a perfectly rational adversary would let us to do. And this observation noise, we have similar results if we consider payoff noise or execution error by the part of the defender. I'll now pass it over to Katie, who will present the real evaluation by the U.S. Coast Guard.
Thank you, Fernando. We had the opportunity to compare actual patrol schedules from the Port of Boston conducted by Coast Guard patrol boats before and after Protect. The x-axis is the day of the week, and the y-axis is the number of times a patrol area is visited for that given day of the week. The y-axis is intentionally left blank for security reasons because this is real data from the Port of Boston. And the values in the graphs are averages of a year's worth of real patrol data. In the pre-protect figure, notice a dearth in patrols. For day 2, there's a dearth of patrols, and day 5, there's an increase in the number of patrols. And the reason for that is on day 2, there was exercises and training that were scheduled that day, and so they couldn't conduct as many patrols on that day. Whereas day 5, Coast Guard reservists were available to come and help out and conduct more patrols on that day. This pattern goes away post-protect. Besides the pattern, notice that the lines in the pre-protect figure tend to vacillate, indicating that some days the higher value targets were visited more often, while on other days they were visited less often, even though their value did not change day to day. We see less of the intersection of lines in the post-protect figure. And also the lines in the lower lines in the post-protect figure are areas that have targets of lower payoff value and are thus not visited as often. So we showed that Protect eliminated the predictable patrol patterns, but the Coast Guard needed a way to evaluate whether or not the actions of our crews were effective. So we devised the Adversarial Perspective Team, made up of terrorism subject matter experts, to conduct an assessment of the patrols before and after Protect, incorporating the adversary's known intent, capabilities, skills, and cultural influences. The Coast Guard applied value-focused thinking to assess discernible changes in tactical deterrence from the APT's recorded observations. Value-focused thinking is a decision theory methodology that assists decision makers in formalizing their process in a quantifiable, defendable, and repeatable process. The value-focused thinking category and weighting structure is driven by the subject matter expert. In that regard, the resulting quantitative process resembles the decision maker's values and even their bias. This framework is particularly relevant in the application of terrorism. So I'd like to note 2 things. The APT was made up of terrorism subject matter experts, and their assessments were conducted as blind evaluations, so only a handful of people knew that they were even out evaluating the boat crews, and those people were not involved with the project at all. The value-focused thinking uncovered positive trends. The deterrence value of Protect patrols as perceived by the APT is generally increasing. The pre-protect deterrence value was 0.45, whereas the post-protect deterrence value was 0.731. This increase in deterrence as perceived by the APT is largely driven by high officer presence from the small boats. 33% of the observed pre-protect small boat patrols had high officer presence, as opposed to 75% of the post-protect patrols. The higher officer presence is likely a result of the trainings, tactics, and procedures that were changes that were implemented from Protect. TTP is one of the best outcomes for the end user. TTP, for years, the boat crews have been told simply to go out and protect our waterways. Little guidance was given on how exactly to do that, what things to do, what things to look for, what things to think about when patrolling the waterways. So Protect was the catalyst that got the key personnel together to get the TTP written so the end user, the frontline defender, could conduct their patrols effectively. Boat crews have now been given clear guidance on how to conduct their patrols through this revised TTP. And this organal change is progress for us, and we consider that to be proven impact. However, the Coast Guard also has a strong desire to quantitatively measure its performance. Because we aren't a public company that can measure in sales or contract dollars, it's more difficult for us to determine how we're doing and measure that. For Protect, we have started to develop the idea of using the Defender utility that Fernando talked about to calculate our measure of effectiveness. Simply put, Protect provides the optimal schedule to which we can compare our suboptimal execution and use that delta to measure our effectiveness. Protect is definitely succeeding in what the Coast Guard needs it to do, which is to appear unpredictable when we patrol. One Coast Guard member was asked if we had acquired a bunch of new patrol boats because the Coast Guard seemed to be everywhere all the time. This is a success for us. Protect received the Coast Guard Operational Excellence Award, which reflects the Coast Guard's recognition of impact and value for Protect. And senior leadership of the Coast Guard recognizes the benefit of Protect in the partnership with academia. This partnership emerged from our need to solve complex problems and the university's need to find worthwhile research problems. For future work, the Coast Guard is moving forward. We are evaluating every possible option to make Protect the enterprise solution for our patrol scheduling. We plan on building out 18 ports a year until the project is complete. Finally, now I'd like to conclude with a pre-recorded message from Coast Guard Northeast Region's 1st District Chief of Response, Captain Tom Vitullo.
The Ports, Waterways, and Coastal Security mission of the United States Coast Guard is one of the primary focuses of the service. It entails the protection of the U.S. maritime domain and the maritime transportation system, and those who live, work, or recreate on or near them. The prevention and disruption of terrorist attacks, sabotage, espionage, or subversive acts, and our ability to respond to and recover from those events that do occur. Conducting ports, waterways, and coastal security missions deter terrorists from using the maritime transportation system as a means for attacks on U.S. territory, population centers, vessels, critical infrastructure, and key resources. The 1st District was fortunate enough to be one of the first ports selected to support a new program aimed at ensuring the U.S. Coast Guard could maximize resources dedicated to the important ports, waterways, and coastal security mission it is tasked with. The Protect model seeks to do just that. A Boston game board was developed for the port with different geographic components. Based on critical infrastructure groupings and the physical layout of the ports, 9 patrol areas were identified. The Protect model initially generated a 60-day optimized random schedule, providing the Coast Guard personnel in Boston the time of day to start the patrol, patrol areas to visit, the sequencing of visits, and what activity to perform at each patrol area. This coordination continues today. Coast Guard Station Boston's leadership and boat crews reported that the schedule was easily implemented and improved their ability to plan and schedule crew rest intervals, required training evolutions, and scheduled boat maintenance. Success was measured not only by the elimination of patrol patterns previously identified, but in addition by exceeding all service visit count requirements without increasing the number of patrol hours or crews, and established a higher revisit rate on critical infrastructure that presented the greatest risk as measured by the Coast Guard's Maritime Security Risk Assessment Model. Given the initial success of PROTECT, Boston continues to use the system to manage its patrol schedule. In February of 2012, PROTECT research focus shifted from Boston to New York City, a more complex area of operations. As more complex defender-attacker strategies and other port, waterways, and coastal security activities are modeled, tested, and determined to be valid for each port, they will be integrated into the overall PROTECT model. The partnership between the Department of Homeland Security's Center of Excellence and the Coast Guard added synergy and excitement into an important but otherwise routine process of conducting harbor patrols to improve maritime domain awareness and enhancing our harbor safety and security. The result was invigorated boat crews, more focused upon providing effective presence, reducing predictability, and enhancing the safety and security within our ports. PROTECT guided patrols became a source of pride for Station Boston crews, and it doesn't get much better than that. PROTECT has also had other positive side effects, such as the development of better tactics, techniques, and procedures. The results have been exceptional, and we continue to refine the products for what I hope will be an eventual service-wide use. I am optimistic that it will be the first of many mutually beneficial projects in the years ahead. PROTECT has provided the Coast Guard with a means to fully randomize and optimize its tactics, techniques, and procedures for conducting critical infrastructure patrols, and was made possible through an effective partnership of operators and academia. It underscores what the Coast Guard and academia can do to protect the homeland in the most efficient and effective manner possible.
Thank you. That concludes our presentation.